I'm hoping that this is our last bit of stuff in chapter 9. We've been talking about specific acid catalysis, and we've talked about how this basically means the acid is not involved in the rate determining step, but rather in an equilibrium that happens before the rate determining step. The specific acid in specific acid catalysis is hydronium, H3O+, or whatever protonated form of the solvent that you're in. However, we're going to see that you can call something specific acid catalysis even if it's not hydronium that does the protonating. As long as the proton transfer step happens before the rate determining step, you're getting basically specific acid catalysis. And I'll show you mathematically how that's the case. So we set up our kinetic scheme like this. You have some starting material that has to get protonated first, and then in a slow step you convert to protonated product, and then you regenerate, then you have the product leave and you regenerate H3O+. And we went through the kinetic analysis. The rate of the reaction, because this is the slow step, should depend on a rate constant times the concentration of protonated R, which you can relate based on our definition of Ka to the amount of starting material R that you have and the amount of hydronium you have in solution. And we're assuming this is taking place in water and the pH is staying constant. And so you can derive an expression for the rate equation that depends on the Ka of your protonated starting material, the concentration of starting material, and the amount of hydronium that you have. All of these terms here that I'm circling are constant, and so the reaction looks like it's first order and depends on the concentration of starting material, which makes sense, but this rate constant depends on the pH. And so a hallmark of specific acid catalysis is this linear dependence on pH. Where the reaction slows, the less and less hydronium you have in solution. All right. Questions about that? So let's set up a situation where we have, instead of hydronium in the pre-equilibrium, let's say we have acid HA does the protonating prior to rate determining step. An example that your text uses is if our acid were acetic acid, and if you dump that in water, remember the pKa of acetic acid is around 4, so if you add HA to unbuffered water, probably you've still mostly got HA in solution instead of hydronium. So let's just set up the same equilibrium where we protonate our starting material and get the conjugate base of our acid. Then in a rate determining step with rate constant K, we generate protonated product, which then reacts quickly with the conjugate base of our acid to generate product and regenerate our acid catalyst. So as we did above, the appearance of our product is going to depend on the rate constant of the rate determining step times the concentration of our protonated starting material. But now the starting material is in equilibrium with our acid. And so if we want to find an expression for concentration of protonated starting material, it's going to look a little different than it did when we were using hydronium as the acid. So the equilibrium constant should be the protonated R group times the concentration of the conjugate base times the concentration in the denominator concentration of HA times the concentration of starting material. And it can be, let's see, yeah, so we can do a little bit of algebra. We want to get RH alone. That means we're going to multiply both sides by the denominator here, HA times R, and then divide both sides by the concentration of A minus. And that will allow us to write a new expression for the rate constant. I'm sorry, for the rate law that depends on the concentration of R, the concentration of the acid, and the concentration of the conjugate base. All right, well, there are a few other things we know that can allow us to eliminate some things from this equation that we don't know very well. So if we write the expression for Ka for our protonated starting material like we did earlier, that's RH plus, oh wait, Ka, sorry. Getting a little crazy. That's R times concentration of H3O plus divided by concentration of RH plus. And we can also know the Ka of our acid, which is going to be H3O plus times concentration of A minus divided by concentration of HA. And one of the things that's apparent right away is that the ratio of HA over A minus is equal to the ratio of H3O plus divided by the equilibrium constant for our acid. So now I can alter my rate law by substituting in this definition, this equality based on our definition for Ka. So that's going to look like this. We keep the R, but then we swap out the HA over A to be H3O plus over Ka of our acid. Okay, and that should start to look a little bit like the expression we derived up here, where we've got in the numerator concentration of hydronium and concentration of starting material. But unlike up there, instead of having just a rate constant and the Ka of our protonated starting material, we have a rate constant, the equilibrium constant for that first step, and then the Ka of our acid. Now, this step may be a little bit difficult to see. As we said above, we defined the equilibrium constant for that first step like this. But if you notice, the RH plus over R term looks a little bit like the reciprocal of this equilibrium constant. And the A minus over HA term looks a lot like this equilibrium constant. So what I want to show you is that our equilibrium constant for that first reaction is equal to the ratio of the Kas for our acid that we've added and then our protonated starting material. And if you don't believe me, just watch. Oops. hydronium cancels out, and we end up with the expression I've given you. Okay, so now I can substitute in this for KEQ in this equation. K times Ka of our acid divided by Ka of our protonated starting material times R times H3O plus, and then times Ka of our acid in the denominator. Those terms cancel each other out, and now we're left with the exact same expression we had before when hydronium was doing the protonating. And this is kind of a surprising result, or at least it was to me, that as long as the acid-base equilibrium happens before the rate determining step, it doesn't matter whether it's an acid you add or hydronium that's doing the protonating. Either way, you get the same answer. And this is reflected in an experiment where you could take the rate of the reaction, K obs. Remember how we simplified this into a pseudo first order equation where K obs equals K times H3O plus divided by Ka over Ka of our protonated starting material. Notice that the concentration of our acid does not appear in that expression. And what that means is that for specific acid catalysis, it doesn't matter how much of our external acid we add, the rate doesn't change. So if we adjusted pH to 6 and then added a ton of our acid, the rate would not change. If we adjusted pH to 2, then the rate's going to be faster because of this equation there, but by changing the concentration of the acid, the rate doesn't change at all. Okay, so the hallmark of specific acid catalysis is that the proton transfer happens prior to the rate determining step. The consequences of that are that the rate depends linearly on pH, and the concentration of acid that you add doesn't matter. Only the pH. Go ahead, Isabella.
Does this mean there has to be water in the reaction for you to use this expression?
Yeah, you're assuming that there's water in the reaction, and that's true for most or some solvent, and that's true. Well, I guess that's stupid to say. That's true in reactions involving water. I think you're envisioning that this situation may not apply to trying to use acids in more nonpolar solvents, and I think you're absolutely right. Other questions? Okay, so we could do the same for specific base catalyzed reactions, but we won't. The math's in your text and you can look at it there. But in the same way, the rate of a specific base catalyzed reaction depends only on pH. Okay, so now we'll go to the second form of acid-base catalysis. This is called general and general acid-base catalysis. And I'm going to just focus on the acid side of things. Anything we do for the acid could be done for bases. This refers to a situation in which the acid is involved in the rate determining step. And we're going to see that therefore the concentration of our acid matters. why do we call it general acid catalysis? Because acids other than the specific acid, which is hydronium, acids other than the specific acid matter. So the hallmark of general acid catalysis is that the concentration of the acid that you add matters. And the reason for that is the acid is involved in the rate determining step. So general acid catalysis often involves proton transfers that are concerted with other mechanistic steps. It almost has to be this way if you want proton transfer to be in the rate determining step, because proton transfer in and of itself is really fast. So sort of the only way to slow it down or make it part of a rate determining is to make it part of the rate determining step by coupling it with a slower step. So an example equation that we can use would be you need some acid and your starting material. In order to allow water to add to your starting material, this would be the slow rate determining step. There would be some rate constant. You form the protonated addition product, and then in a subsequent step that is fast, you regenerate your acid and your final product. All right. And that may be a little fast, and it may be difficult to see because we're trying to be as general as possible. One of the things you could imagine as an example of this is perhaps hydration of ketones under acidic conditions, and we'll show you that in just a second. Or actually, maybe let's show you an example of that now. So, and this is meant to illustrate a mechanistic hypothesis. We're not saying anything yet about what the data actually say for what acetone hydration, for the mechanism that acetone hydration actually goes through. But we could propose a general acid mechanism wherein a nucleophile attacks at the same time as the carbonyl is getting protonated by the acid that you add. And presumably the justification for this would be that water is not a good enough nucleophile to add to the neutral carbonyl on its own. You end up with this protonated hydration product, and then in a second step, the conjugate that is fast, the conjugate base of your acid removes a proton from the oxonium ion, and you regenerate your acid. So this is an example of the acid involved in the rate determining step. Fortunately, the math is a little bit simpler here. So the appearance of our product is going to, in the case of the reaction that we've shown, going to depend on the concentration of our acid and the concentration of our starting material, and I suppose the concentration of water, though we're actually going to fold that into our rate constant, if that's okay. Because in water, if your solvent is water, the concentration of water is like 55 molar, and it doesn't change through the course of the reaction. So, K with the little prime thing there is K times the concentration of water, just to keep you oriented. And if you forget that, that's totally fine. So, because HA is a catalyst, its concentration doesn't change. over the course of the reaction. And so that can be folded into the rate constant as well to give you this pseudo first order rate expression where your rate constant depends on the concentration of acid. Okay? So if you, based on this, if you were to plot K obs versus the acid concentration, you would expect to see a linear plot with slope of 1. All right, questions so far? Now, one thing we should be aware of is the fact that pH can matter here too, because you know that the concentration of HA that's available to you, it does depend on the amount of hydronium present in solution. All right? So we could substitute out for HA the following expression, H3O plus times A minus divided by HA. Oops. Divided by Ka. And in that case, if we put that back in, K obs in our expression here would be equal to rate constant times H3O plus times A minus divided by Ka of the acid HA. Now contrast that with the expression we derived earlier. With the expression we derived earlier, H3O was in the rate expression, but A minus was not. And the reason for that is that the starting material is involved, the acid is involved in the rate determining step. All right. Questions about that? Let's just think through how pH would change the rate of the reaction. And we're going to do log of K obs versus log, or rather pH is already a logarithm. And suppose your acid is acetic acid, and you put in a certain amount. If you adjust the pH lower, what should that do for your reaction? Go ahead.
Is the protonated or deprotonated form accepted?
Well, the protonated form, as we've set it up, our acid HA is the thing that does the protonating.
In that case, then lowering the pH will increase
To a point, right? So if you start out at pH like 10, where there's, under those conditions, if we're saying that our acid is acetic acid, the pKa there is about 4, which means that at pH 10, you've got 100% deprotonated species. So then your catalysis should be pretty low, right? And if you start to increase, or rather decrease the pH, let's suppose this is pH 4 and 7 or something like that. As you approach the pKa of the acid, you have a somewhat linear relationship because as you lower the pH, you are changing how much acid you have in solution. But at a certain point, you level off, and subsequent changes in pH don't matter anymore. And that breaking point where you level off is usually the pKa of the acid. So this is another characteristic of general acid catalysis that differs from specific acid catalysis. With specific acid catalysis, you had a linear dependence upon pH across the whole domain of pH. With general acid catalysis, you have a linear dependence on pH until you get to the pK of the acid, and then after that, as you go lower, there's no rate acceleration. But there is a linear dependence on the amount of acid that you add. Okay. One thing your text points out that is a little bit confusing to me is that because we have these two equivalent expressions for the rate constant, and maybe I'll just rewrite our rate law to be as clear as possible. Because we've got K times HA times starting material R, or K times H3O plus times A minus divided by Ka of your acid times R. Because you've got these equivalent expressions, we can't actually tell if it's H3O plus or HA doing the protonating in the rate determining step. For example, we've shown you that mechanism. I showed you the mechanism for hydration of a ketone where the acid is involved in the rate determining step. And you could propose an alternative mechanism wherein you would have let's see, let me rephrase this because I think I got it a little bit wrong. You can't tell if it's HA doing the protonating in the rate determining step or H3O protonating and A minus deprotonating in the same step. So what I'm about to show you is a kinetically equivalent option that you really can't tell the difference, at least in terms of a kinetic mechanism or in terms of rate laws. They would have the same rate law. So here our conjugate base of our acid is involved in the slow rate determining step. Oops, I wanted red. We remove a proton, we attack the ketone, we break the pi bond, and then we protonate the incipient negative charge on the oxygen to get the hydrated molecule and regenerate our acid. The rate laws for those two scenarios would be exactly the same, and so you can't tell the difference between them. The first one is the one we did before, yeah. This is our first scenario where it's just where you have this acid is involved in the rate determining step, not hydronium. And then you have water attacking. But we can't tell the difference between that and the alternative where hydronium does the protonating at the same time as the conjugate base of our acid deprotonates water. Okay? So who cares? Well, first, if you notice, go ahead. Would the pH aspect discern between these two mechanisms? No, because the pH is going to control the relative amounts of these two molecules in solution, right? They're related by the Ka. And so presumably if you lower the pH beyond a certain point, you may increase your amount of hydronium, but you're going to dramatically decrease your amount of conjugate base. Yeah. So they would offset each other. Yeah, really kind of weird. Now, when I look at this, I say, well, first let me just put for the notes, kinetically equivalent. When I look at this, I say, okay, you've got a lot of things going on here. Bimolecular reactions where two molecules encounter each other in the rate determining step are well known. Termolecular reactions where three things have to find each other in the rate determining step do exist, but they're less common because it takes longer for three things to find each other in a solution where everything's bumping around. And then here you've got four things finding each other, which seems really unlikely. And I agree with you that it is. But remember that enzymes can place acidic and basic functional groups in the right places already, prepaying the entropic cost of activation, and then your substrate binds, and then everything's present for these kinds of concerted steps. So you may find that general acid catalysis is a feature of many enzymes. Now, specific acid catalysis can be a feature of enzymes too, particularly if the protonation doesn't happen during the rate determining step. Okay? So as you learn more about enzymes, you may find examples of specific acid versus specific base catalysis. The consequences are there and you should be aware of them, but the most important thing to remember is for specific acid, the acid's not in the rate determining step, and for general acid base, it is in the rate determining step. All right. So here are your text highlights a few let's see, anything else you want to say about that? I actually don't know if probably need to not say anything more about that. There's some potential energy surfaces in your text that might be worth looking at, but I think what I want to spend the rest of our time talking about is enzyme kinetics, if that's okay. How many of you have heard of Michaelis-Menten kinetics for enzymes? Sound familiar? This looks like Michaelis, like Professor Michaelis, but people call it Michaelis-Menten kinetics. For some people that didn't know David before he applied here, when we were considering his application, some of them pronounced his last name Michaelis, which it isn't. It's Michaelis. So who knows? This is named after the two people that developed it. Essentially, it's it describes enzyme binding to substrate, a steady state approximation of the concentration of enzyme and substrate, and then conversion of that enzyme substrate complex to product. So you have the enzyme and the substrate. There is an equilibrium step with a forward rate and a reverse rate to generate the so-called enzyme substrate complex. So this is binding of the substrate by the enzyme in a pre-equilibrium that is fast. And then conversion of substrate into product. This is enzyme product complex. And the conversion of substrate into product is the rate determining step. We're assuming that that happens in a single step. You don't have to assume that, but it makes the math easier if you do. And then finally, fast dissociation of enzyme and product. All right, so if we wanted to talk about the rate of appearance of our product as a function of time, that should only depend on the rate constant for our reaction. People call that K-cat because they like cats, or alternatively because it's the reaction that's catalyzed. K-cat times the concentration of enzyme substrate complex. But the problem is we don't know this. And it's difficult, it may be difficult to measure. So, to the rescue comes steady state approximation. I don't do enough cartooning during this class. I always do in undergrad class. But anyway, superhero steady state approximation. We're going to say that the concentration of enzyme substrate at any given time is small because it's a catalyst, and because the enzyme is a catalyst, and therefore the change in the concentration must necessarily be small. And so that allows us then to write a steady state equation like we've done before, where we say, okay, the rate of change in the concentration of enzyme substrate complex is going to equal 0, but that rate has various contributing factors. One of them is the forward binding rate constant. One of them that causes disappearance of the enzyme substrate complex is the reverse of the binding constant, and then, of course, conversion of the enzyme substrate complex into product also causes this to disappear. A challenge with what we've got here is we don't know at any given point what the concentration of enzyme is. And so we've got one equation with two unknowns. However, we do know in experiments, we do know how much total enzyme there is, which we're going to call concentration of enzyme with the subscript 0. That's going to equal the that's going to equal the amount of unbound enzyme plus the amount of bound enzyme, because that's all the enzyme you've got. I suppose for this you have to assume that the amount of enzyme product is basically 0 because this step is fast. And in many cases we'll do these experiments in the early stages of the reaction where there's not a lot of product accumulated yet. So we can actually write an expression for the concentration of enzyme that is equal to the amount of enzyme we added at the beginning minus the amount of enzyme substrate complex at any given time. This then allows us to do the following. Oops. And now we've got one equation and one unknown. We now know we know how much enzyme we put in. The only thing we don't know is the concentration of enzyme substrate complex. So we can do a little bit of magic here, and it's just algebra, so I think I'm going to abbreviate that. You've just got to isolate variables and get ES concentration on one side of the equation. If you have a hard time seeing this, I can show it to you, but I think you should be able to figure it out, so we won't spend time now doing it. Oh, did anybody catch what I screwed up on? I'm missing the concentration of S there. Shame on me. In the denominator, we're going to have K1 times the concentration of substrate plus K minus 1 plus K cat. And then, if you forgot where it was we started, we've solved for the concentration of enzyme substrate complex. So now we can take that expression and put it here. And now we're going to do something that's annoying. We're going to multiply the numerator and the denominator by 1 over K1. That's going to get rid of it there and there, but it's going to change the form of those last two rate constants in the denominator. So in the numerator, we now have Kcat, enzyme concentration, total enzyme concentration, substrate concentration. In the denominator, we again have substrate concentration, and then we have this weird K minus 1 plus Kcat divided by K1. And that, my dear friends, is what we call the Michaelis constant, or Km. And that is difficult to interpret. Understand, though, that K1 is if you look at our initial rate expression, K1 is multiplied by concentrations of two different molecules. So K1 has to have units of m to the minus 2 and then seconds, per seconds. K minus 1 is a unimolecular rate constant because it involves the enzyme substrate complex dissociating. So that should have units of per molar per second. And then Kcat is also a unimolecular rate constant, which describes the conversion of enzyme substrate complex to enzyme product complex. That's also got units of m to the minus 1 and seconds to the minus 1. So overall, Km has units of molar. It has concentration units. That should make sense because in the denominator we add Km to the concentration of substrate. All right. Questions so far? So what does Km mean? And the answer is it depends. So we're going to start with what the heck Kcat means. Kcat is very simple. It's in units of per molar per second, and it describes conversion of the enzyme substrate complex into product. And so we're going to also call this I think your text is wrong on this. Hold off on that. So Kcat describes how fast the reaction goes. Km, its meaning depends. And so let's look at this and let's imagine a situation where K minus 1 is way, way greater than K cat. That's the description of a really cruddy enzyme, because that would mean that it's way faster for the enzyme substrate complex to go here to dissociate than to go on to enzyme product complex.
So such an enzyme pretty much loses more ground than it gains.
Well, that would depend on the binding, on the, it would depend on what K minus 1 and K1 are, right? Because if K minus 1 is much greater than K cat, then Km is a lot like K minus 1 over K1, which is equal to the dissociation constant, or the binding constant between enzyme and substrate. So even if K cat is really, really low, it's possible that K1 is so fast
Then it goes forward without
that the reaction still goes forward because the enzyme substrate complex lasts so long. We're just talking about the relative speeds of K cat versus K minus 1.
and K minus 1 is the dissociation.
Is the off rate. Yep, the off rate, or the...
Not the reverse product to substrate.
Right, not the reverse product. So K1 is the forward rate of binding, K minus 1 is the reverse rate of binding. So under some conditions, you can think of Km like a dissociation constant, and like dissociation constants, it has units of molar. But there's a alternative regime in which K cat is much, much greater than K1. Then Km resembles K cat over K1. And how do you interpret that? What units does it have? It still has units of molar. It's not clear what that means. But it doesn't mean KD, whatever it means. All right? So if you hear people interpreting the Michaelis constant as a binding constant, that's only accurate under certain situations. So we are out of time for today. There's only a few more things to say on this subject, which I will deal with at the beginning of the next lecture. So it's been fun and it's been real, and we'll continue to be around and correspond, so this is not goodbye. I will see you next on the web.